Okay, folks. How's everyone doing? It's hot. It's really disgustingly hot. My office is freezing. That's why no one wanted it. I'm like, yes. Okay. Everyone turned in check-ins. Who wants to pass the class? Okay. Even if you don't want to pass the class, I still recommend it. Homework's here. You're not getting anything back right now because I'm still in the process of taking everything that's graded and putting it into your check-in. So that's all going to happen at once. There's a lot. I'm trying to get through it. I apologize. We'll see. We'll see.
We get homework for that, right?
No, I still have homework. Okay. Any questions before we get started? I don't think there's any staplers in there, unfortunately.
No, I'm so
Yeah.
sorry.
It's okay. You can just, if you want, you can just. Okay. What's this? Pluto. Pluto in both cases, right? Okay. So we're going to talk about Pluto today. That's basically going to finish up our discussion of icy terrestrial planets, planets without atmospheres, as far as we think of them. And then we're going to start talking about atmospheres because they're awesome. They're the best part. In order to understand atmospheres, we'll have to understand light. And if you've never sat down and thought about what it is, light is, that will be weird. Okay? So we'll talk about color. We'll talk about the structure of the atmosphere, and then we'll apply it to all of the planets. We have the coolest atmosphere, in my opinion, but we'll look at Mars, we'll look at Jupiter, we'll look at Saturn, and then we'll do all the outer planets. We'll do some small objects, like what are comets, what are asteroids, and then we'll finish off the semester by talking about how did the solar system form. Okay? For week 6, I think there's like 10 weeks left. It's pretty good. If you haven't been to the observatory, that's okay. If your schedule never works out, that's totally fine. But if you feel like, oh, I'm robbed of extra credit, do you guys know what this month is? If you like one, right? You ever seen these on TikTok? Okay, you're typing the letters GEO. She does really incredible TikToks that every single day is a different spooky haunted hydrology thing. So it's spooky lake, but sometimes it's a river, whatever. Anyway, we'll do 30 seconds. And there's one per, oh, where'd it go?
Yes, hello. It's October 1st. Do you know what that means? It's Spooky Lake Month, where we're doing 31 days of haunted hydrology. And today, I want to talk about what might be the most morbid mystery of any lake in the world. Located over 16,000 feet above sea level in the Himalayan mountains, this lake is more of a frozen puddle for most of the year. But as the seasons warm and the ice begins to melt, what's revealed are hundreds of human skeletons.
Pretty good teaser, right? Eh? Now you want to watch it. Okay, don't watch it in class. Okay, so here's what I want you to do. If you want to, you can watch them. I would recommend watching. They're one per day, less than 5 minutes, and you learn something about planetary science. They trick you into learning, and at the end of it, you write about the one you like the most. Is that fair? Okay. Okay. Do you want to work at the observatory? You ever thought about that as a possibility? What we're doing? Okay, good hand right away. Oh, you have a question? No. Maximum. So we open applications only once per quarter, and then we close them. Because I have to sift through and delete lots of people who are unqualified. But by taking a class like this, you are qualified. What does that mean? You will learn how to operate the telescopes. You will learn what is in the night sky. But most importantly, you'll learn how to talk to people about the night sky. So generally, it's a science communication position. You're not gonna be doing research. You don't have to sit at a computer the whole time. It's, outdoors at night. So if you're interested, this opens wherever CSU jobs appear, and then it'll close. If you have questions, you can ask. Yeah.
There's GPA requirement.
There's no requirement.
So you have to like, you have to be in the class.
I recommend that people have done this class. People will apply without being in this class. Yeah.
I was guessing because it's about this was required for
They don't all require federal work study, but oftentimes if you have federal work study, it will kind of boost you because they like to, yeah.
Okay, then maybe. I'll write that down if I remember it. Yeah.
On top of the federal work study, from what I heard, is they're not hiring unless you have that because there's just no budget for more student workers.
Okay. There you go. This is a different budget, so I don't know how that works. This is a very unique position. We get a limited number of hires per 2-year period. Preference tends to be given to folks who are not on their way out. Like if we can train you how to use the telescopes and you want to be here for multiple years, we'll take that into consideration. That's not to say that you shouldn't apply as a senior. It's just, Yeah. Okay. Good. Yeah.
handshake.
Good question. What was that?
I had employment opportunities.
Yeah. All right. So why spend so much time on Pluto? We talked a little bit about this last time. Weeks 3 and 4, we really set the tone for understanding the solar system. And then we made modifications. What was the primary modification between the terrestrial planets like Mars, Mercury, Earth, and the outer moons? What's the major thing we want to consider here?
I'm not sure if it says the size, we talk about the size of all things.
The size is definitely getting smaller, and yet they're active.
They're made of ice and rock.
They're made of ice instead of rock. That still doesn't explain why they're active. Why are these objects that I claimed should not be active based on how small they are? Why are they active? Yeah.
Tidal heating?
Tidal heating. Okay. Tidal heating was really important. Now, the fact that they're made of ice at all is really important too, because ice can melt before rocks do. Right? You'd be really upset. Your coffee with ice in it, the cup melted before the ice cubes did. Right? That makes sense? So this whole world, this icy world outside of Jupiter, starting at Jupiter and going out into the solar system, all of the objects there play by slightly different rules. But we're going to try and understand all of them encapsulated in this body called Pluto. Okay? We'll have another homework, you'll hopefully seen it today, that'll kind of test some of those concepts more. A lot of the same questions that you've seen before, in exactly the same context, but just for icy bodies. Okay. Okay. What did we know? Good start. What did we know before New Horizons got to Pluto?
It was light and dark.
Light and dark, yeah. Remember those Hubble images? They're just horrible, that are just like, okay, spots. Yeah. It had a moon. Do you remember the name? Aaron, very good. Anything else?
Small.
Small, yeah, real small. Yeah.
Orbit was weird, cross in front of it.
Orbit was real weird, like a spinning wheel, right? Kind of tilted on its side. Anything else? That's basically what I wanted to start with. Weird. Doesn't look like the nearby gas giants, small and icy, right? And it's only 6 times bigger than its moon. So for comparison, there's some other objects in their moons. So we're about 81 times bigger, and Jupiter is, well, Jupiter. Okay. So that's a really small size comparison between the two bodies. That's like, I mean, I'm trying to think of what a sixth of a foot. Right? That's like pretty large. Okay. Here's how we're arriving with the spacecraft. As I mentioned before, on this close approach, we're going to go through the orbit of Charon. We're going to have to go behind the shadow of Pluto. That allows us to look back at the planet and just see only the atmosphere. Right? We're in this, yeah.
It was a 9-year from launch to getting there, right? Something like that. How do they calculate exactly threading the needle like that? 9 years in advance.
Yeah, it's hard. So the spacecraft part of this is really cool. The engineers are amazing. They use something called Spacecraft Toolkit, and it's like a model. It's like a Google Maps, but in 3 dimensions. And the way that you can navigate is because the stars don't move. So every spacecraft has a set of 3 cameras that are called the star finders, and they just point like this. One goes this way, one goes that way, one goes this way. And based on where they see stars in the sky, they can figure out which orientation they're pointing and which direction they're going. It's crazy. The technology is really superb. And so then you start shooting, and you basically pull the gas for a little while, and then you turn it off. And you say, where am I now? Because sometimes you aim to go over there and you kind of end up a little bit over there. So you never like do a full burn, you do tiny little burns. They're called trajectory course maneuvers. And you just keep changing a little bit how you're moving. And because you know how fast you're going, because you know where you are and how much you weigh, you can figure out where you'll be in the future using Newton's law. So this computer program does it. We trust the spacecraft people because they got us there. The reason why this is really important to know ahead of time, as we alluded to, we took images and we found just a few days before there was extra moons, right? So we wanted to make sure as we thread this needle, there's not like a moon right there that we smash into and ruin the whole spacecraft. Okay, there's the 2 other ones, Styx and Kerberos. Styx is actually interior to these other ones we knew about, Hydra and Nix. So we could study a lot of these objects, but the only 2 that we really got good images of were these larger 2. And this is, excuse me, the correct size comparison. This is the size comparison for all of them. Pluto, not even as big as the US, tiny. But you could basically drive this whole system in like 50 hours. Okay. You're moving at about 33,000 miles an hour, even that far out. New Horizons is the fastest thing we've ever launched until Bepi Colombo, which is headed towards Mercury. That it just like very recently was launched, and now it takes the fastest man-made object title. But you'll see in this very short exposure, we're going to go through, not a video, we're going to go through the shadow of both of them. We're going to look for atmospheres in both. And we're going to, here, we're looking at the planet as it's illuminated. As we get close, this is where you get the highest resolution images. You get the closest to it. And then by the time you're back here, it's too dark for us to see anything. Similarly, we're gonna try and look at Charon here. So we'll look Pluto, Charon, get a really good map of Pluto, and then pass through the shadow of both of them. And then for years, we'll send the data back. Okay? The reason that it takes years to do so, there's no Google Fiber out there. So it's all by radio. And radio is not very efficient. So you have data rate constrictions that are really small, like megabits per second, and you take gigabits of data. And so now you have to wait. You put it all in the onboard computers, and then you wait. Because after it goes through the Pluto system, it's not taking data anymore. It doesn't care. And so its whole job is just send back data.
How fast the other one pick the recording?
Good question. I'll find it out, but it's fast. Yeah, Bebe Colombo needed to go faster in order to get towards Mercury. When do we get back the pictures of Pluto? So I believe so here's the launch. Sick. I love launch photos anyway. I believe the launch was 2004 or something. Maybe 2006. And then we arrived in 2015. You got the first images right away. And so what they did is the engineers were like, well, we need to send back something to demonstrate why we spent all this money. So they prioritize, okay, send this camera data down first, right? If you're going to send any information, send this data first, and then this data, and then this data, right? And so we got images right away, but it took another 2 years to get all of them. Cool. Okay. Folks not asleep yet? Let's think about what it should look like. That's the beautiful image of Pluto. If the temperature at Pluto is 40 degrees Kelvin or minus 233 degrees C. Now I realize neither of those are freedom units. But let's just remember that water freezes at 0 degrees Celsius, 0 degrees C. What state of water do we expect to find on the surface? A, solid water. Wait, hold on. I forgot to open this up. Fuck. Hold on. I hear you clicking. Wait. All right. It's stressing me out. Solid water, ice, partially solid, partially liquid, fully liquid, partially gas, or fully gas. Hey, looks like I didn't trick most of you. What's the right answer? What? Ice. Yeah, it's really cold. Super cold. We expect ice. It would be weird to see anything else, right? You all agree? It would be weird to see anything else.
You said it freezes at 0 Celsius.
Yeah.
And then after that, because it's negative now, so it's
Yeah, yeah. That would be a lot colder, right? So we have no reason to expect anything but ice, right? Making sure we all agree. Okay, let's try it again. Come on. All right. Based on what we know in class, what should we expect Pluto to look like? A, smooth ice-covered surface. B, heavily cratered ice-covered surface. C, volcanically active rocky surface. D, thick Jupiter-like atmosphere surrounding a small icy core. E, thick Jupiter-like atmosphere surrounding a small rocky core. Bad reading. right, click in if you want to. 3, 2, 1. All right. Most people picked heavily cratered rocky surface. Ice covered surface. Heavily cratered ice covered surface. B. Most people picked B. Why would that be? Someone had it top there. Yeah.
Ice covered because, like you said, it was negative 233 degrees Celsius, so it's obviously very cold.
Mhm.
And I feel like it would be a lot closer to where the year was coming into the solar system.
Okay.
Because like we saw that there was like a bunch of other like dwarf planets that are nearby Pluto. And
Okay.
like that, those are
So that's the reason why it would be heavily cratered. So what about like using the ideas that we had for small bodies previously? Do we expect things like erosion here? Right? Do we expect volcans? Yeah, right. We expect tectonics. Dead planet, right? So if it's dead, it just accrues impacts over and over and over. Right? Okay. So that's our expectation. And folks were writing papers up until like March 2015, including some colleagues of mine in grad school. And they were like, trying to submit this paper because, you know, once they get there, if it's wrong, then no one cares. But if it's right, then I look really smart. Like predicting something before you see it, right? So this is you know, the artist impression. And they're like heavily cratered, gross looking, icy body. Okay. Let's see what it looked like. Oh, that is something I've already written. Okay. Here's where we're approaching. These are those close approach images. Kind of better. Better than the spotty black and white images of Hubble. So it's rotating as we're getting closer. Its day is about 9 days. And so you can see here, time is changing. This one to that one, to this one, to that one, to this one, to that one. So it's rotating as we're getting closer. And then this is the video. We're gonna watch this a bunch of times. Okay. Let's go back. Okay. So this is upon closest approach. We can already see in the colors here, a really bright light region next to a dark region. Very similar to how we saw with the Hubble images. Okay. The colors here are real. This is really what Pluto looks like. So it's not gray like you would expect the moon to look like. And that's pretty weird already. As we get closer, come on now. All right, as we get closer, we're going to view it from different angles. Let me stop. Embarrassment. Okay, there's the atmosphere as seen from behind. What's that thing? The sun. Very good. Okay. Did you see a second body in there as we passed behind it?
there was
Yeah.
oh there
Oh, okay. So that second body that you saw for like a second, that's Charon. And we're going to look at images of that as well. We don't, as we pass behind it this here, you know, you can kind of see the Charon's going to come this way or wait. Yeah. Okay, good. Whew. So now we're heading behind the sun, and then we're going to head behind Charon, but it won't happen in this video. Newsflash, no atmosphere there. Okay, one more thing. Let's see if I can stop this before we get in. All right, that's perfect. Stay right there. Okay. There we go. That's pretty cool, right? Any features you see? Crater. Good. One. Snow. Smooth. Okay. Anyone have smooth for the last question we asked, the quick question? That's right. Definitely smooth looking in some places. It's cratered in others, but it doesn't look like heavily cratered everywhere. Right? There's like this region over here. That's a big old crater for sure. Big old crater. Maybe some one that's over here. But like, I don't even see any in there.
You have what's in your servers?
Yeah, how the hell could that be? This thing is 4.5 billion years old. It doesn't have tidal heating. Okay, that's weird. So here's what it looks like. The colors are stretched here because you want to be able to see contrast a little better. Okay. And this is the highest res photo. It doesn't look good on the screen, I'll tell you that much. But when you zoom in, it's pretty sick. You can download one of these yourself. They come in like massive file formats, like 10K by 10K. And you can just keep zooming. And if you look in this region here, this is called Sputnik Planitia. Doesn't look like there's any craters. There's a marked difference in the craters of this area and this one. There's tons of craters over here. Kind of hard to see. You can see some of the brighter ones. Nothing over here. Okay, so we've seen craters. We've seen smooth areas. Do you see anything else?
Are the lines tectonic?
Yeah, right? What the hell's that? Oh, we didn't expect to see tectonics, and yet they look tectonic-y. Okay, anything else?
There's slightly.
What do you mean by that?
I guess they might not be tectonic, but erosion because of how we can see its atmosphere. So I would assume there would be some erosion.
Oh, interesting. So we saw the atmosphere in that close approach video. So maybe there's erosion. That's a good inference. I'm not sure that I would see, like, so are you thinking about this or are you thinking about this?
I guess I think like one of
The lines on the side here. Or here.
Yeah.
Yeah, so this is certainly a tectonic feature that comes from the thing cooling. Okay. We're gonna see some really weird stuff on this planet, like water that acts like rock. Yeah. Here. Yeah, like here. So like this stuff. Okay, we're gonna zoom into that area. We're gonna zoom into that area for sure because it's fascinating. If you're looking very carefully, and you may not be able to do it here, we're also gonna zoom into this area that's sort of textured and cantaloupe looking. Right? Anytime we see cantaloupes, we want to know that like an ice flow, like we saw on Europa and Enceladus. Okay. So this is how we think the composition goes. In the interior is probably rock. And then there is a big mantle, like it's, the word is incorrect here, but it's not a subsurface ocean. It's water, it's solid. Okay. And then floating on top of that is frozen nitrogen. Does that make sense? Okay. Frozen nitrogen, like N2, like what you're breathing right now, but it's so cold there that the nitrogen condenses and collects on this body. Okay. The density here is about 50-50 ice and rock, 2 grams per cubic centimeter. So as much rock there is like ice, whether that's water ice, whether that's nitrogen. Okay. Here's the whole planet. Well, sorry. Here's all of the data at once, wrapped out. So this will be like latitude, and this would be longitude, just like if you were looking at a map. The parts up here, we couldn't see that high up. Fly over. And then as it was rotating, we saw that view on the closest approach. And then this is those earlier maps that I was showing you as we were getting closer and it was rotating. So we get like fuzzier data out here, but you can still kind of use it. Like that's clearly a big old circle, right? So this thing right here, probably some impact structure of some kind. Let's look at this region right here, Sputnik Planitia. It's pretty, right? These images will mostly be in black and white because that's the imager, but you're not getting much more information from color in those circumstances. But this is not what it would look like in real life. Right, it has the color. Okay, so you have these regions up here. Does that look reminiscent of anything?
Kind of like ice cracking.
Ice cracking, okay, okay. What do you mean by ice cracking? Like, and where?
Both the Antarctic and like.
Oh, right, right. So like the edge of like an ice cap or something. Yeah, yeah, yeah. I see that. I see that for sure.
Which looks all what's outside of this one.
Yeah, this looks softer than this is, right? That's the funny thing that your brain can do is like, you know exactly what it would be like to lick Pluto. Because you see it and you're like, I know what the texture is. You don't know what it would taste like because you've never licked nitrogen before, but it would be cool. And then this region here, yeah, really looks like, in my mind, it reminds me a lot of the highlands on the moon, right? Something that really looks in a lot of ways like a bunch of mountains or like mountainous region, right? Because you can see the sun's coming from this direction and these are all shadowed. Now, this is just missing data. This isn't like bad, right? This is how they take these strips of data. You can see that there is real texture here associated with the planet having higher and lower points. Let's zoom in again to this region. We really want to understand this. Okay, so you can see this stuff down here too. See these features? See these giant cells? This is a nitrogen ice lake that is warmly convecting. So it's hotter below this lake. And the nitrogen ice is churning and resurfacing this entire thing. So even these ones right here, these are mountains made of ice. Water ice. Okay. That's another image in enhanced color. This tells us a little bit about the composition. So now you're looking at the reds are telling you about complex hydrocarbons. What that basically means is start with something like methane and then just let it evolve. Like, like when you burn something and you get that like brown soot, those are complex hydrocarbons. So it's not from burning, but it's a very similar process here in this part. And even down here, this is the result of these complex hydrocarbons being made in the atmosphere and then sedimenting out and falling on the ground and never being resurfaced. Whereas this is incredibly smooth and incredibly, these ice flow looking features, they are removing anything that falls onto the surface. Even if you smash into it with an asteroid, if it's not within the last 100 million years, that surface is going to be removed. Okay. So that's Sputnik Planum, very young terrain. This is Cthulhu Regio, much older terrain. They suspect that this region is near 4 billion years old. Basically, as soon as you make Pluto, this is undisturbed. And yet, Sputnik Planum is very young. Okay, cool picture, right? Questions about this before we go on? Here's all the craters they mapped. Probably a grad student when sat down, like stared by eye, tried to find all of the little holes in the picture. And they found 0 in this region. Not few, 0. So like I said before, in the Cthulhu region, you have tons of craters per unit area. So this is probably a very, very old surface. And just next door, just right even here on the boundary, no discernible craters. Have you ever seen this type of polygonal to ovoid shaped cells or segments I almost always talk about it, but it may not be in your mind right now. It's still food, folks. It's always food. It's always food. It's miso soup. No one like that. Okay, this is a photo of miso soup. So if you decide to go have sushi tonight and you get miso soup and you don't move it, it starts mixed. And then because it's hot, it will settle in some places and rise in others. The places where it's rising, like here and here and here, it's not dragging up the settled miso with it. Right? And so the miso settles in these other portions. Let's go back now. This is the same process. It forms these cells where at the edges, you either have material sinking, right, in some cases, or rising in other cases, right? And that's how you form these cells all over the place. Right? See all these cells? Okay. There's a simulation here, but I don't think you care about that. Okay, what's this? Same region of the planet. Yeah. Mountains. Yeah. Yeah, the color is very similar to that, actually. I don't think it's made of metal. I believe these mountains are made of water ice. So on Pluto, it's so cold that nitrogen ice can act like water. And it's so cold that water ice can act like rock. Okay. So what you see here, this type of feature, is probably like a mountain in the middle of what we call like a nitrogen or a CO ice field. You might even see on the surface, you see this like weird texture? Or remind you of anything? What's that? It looks like sand. Yeah. So there is a very, very thin atmosphere at Pluto, and there is erosion. And it's pushing ice into like dune-like structures. Yeah. That is a very good question. I believe it's hard. Yeah, I believe you could stand on this. It's weird, right? Because Pluto is not, it's small, like small. So you are not necessarily just going to crush it because you're standing on it, right? Whereas if we stand on the moon, you know, anything we stand up there, you can jump and you can jump much higher because the object's smaller, so gravity's pulling you less. So the reason why you would crush the ice is because something's pulling you down, right? Now, if you were to stomp on it, you could probably break through the ice. But I believe it's not like thin layer and then water. It's like solid state convection, which is kind of a weird concept. But no, not mushy. Mushy, you want to go to Titan. Yeah. Mushy, actually, when we landed on Titan, it was too sticky. And we like wanted to move the thing that we sent. We couldn't. Okay. Cool. All right, here's the Earth equivalent. This is in Antarctica. So this is like a mountain. This happens all the time. Mountains just living their best life. And then water is all around them and it decides to freeze. And this is all that's left. So if you remove the water, this keeps going down. And very similar, if I go back here, right, just imagine that's what you're seeing from above. The mountain of ice. And that ice, remember, goes way, when we were talking about the layers, right? The top layer is nitrogen. Below that is ice. But it's ice that's acting like rock. So this is just a piece of the upper crust poking through, right? There? It's kind of weird, yeah. This one here? Yeah. So this inset is this one, right? And so this would be like a mountain chain in the way that we think about mountains on Earth. And the composition here is very similar to the composition here because the colors are the same. That's what the colors are telling you. not just it's red, but it's really telling you that it's made of water ice. And so this thing here too this is the water ice thing, and then this is some nitrogen ice feature. Or CO ice. Okay. We also see icebergs and stuff like that in the same region. Cool. Whoops, I missed that one. All right. And we see flowing ice cells. So you see the nitrogen ice is carving, just like we saw glaciers form from water ice carving through rock here on Earth. So whether that's at Half Dome in Yosemite, or if you look up the word fjord in Norway, those are all these carved features due to moving ice. And similarly, this ice flows, like you're not going to stand there and watch it flow, but over the course of probably hundreds of days, you're going to watch individual pieces of ice flow into these regions and cut them up. Okay, what's this? What? No, this is still in Pluto. Excuse me?
Is this that a moving part?
Not exactly. You may be asking yourself, what am I trying to get you to look at? I'm getting you to look at this. Yeah, so there's like something that is going up and then a big empty part in the middle. We think this is a cryovolcano. There it is. Perhaps an extinct one. Could be a real volcano, but that's kind of a weird word to say because the thing that would be spewing out of it would be liquid water. And you don't think of that as lava, right? Okay, and then I promised you this. What's that? Yeah, that's erosional features. Remember I told you there's this like weird cantaloupe texture? Well, that's what you're seeing there. And that's real, like these are like textured ice dunes. So not sand dunes, but ice dunes. Come on now. Weird. All right, one more. These are sublimation pits. So these are little dots. So if you have, say, a surface of ice and it's uniformly cold, but maybe in one region you have something that is like not as strong. So let's say the ice is weaker in some places, then the top can fall out, right? And as it falls out, it reveals ice underneath that then evaporates and comes out of the hole. So we see these sublimation pits all over the place. And this is another erosional feature. This is an example of a sublimation pit that we see on a comet. So we sent a spacecraft to a comet. And what you can see is down this hole, when it becomes exposed to light, it immediately starts sublimating. And so the material that's in the hole starts to come out and makes the pit deeper. Okay. What do you see here? Yeah. Yeah, those are mountains. Those are tall mountains too, right?
Looking at Pluto,
Mhm.
are you still looking at Pluto?
Yeah.
Yes, the two different type of texture and surface.
Yeah, this is still that edge of that weird textured terrain. These are those icy mountains. So this is your CO or N2 ice. Yeah, what's that? Yeah, what's that? Is that an artist's impression? Oh, this is real data. This is the real atmosphere. Okay, surface temperature is 40 degrees. These are layers of haze in the atmosphere. You can see, so what is a layer of haze? A layer of haze is produced, like we talked a little bit earlier, by complex, they're basically complex molecules. Get the other word that I said. Just think to yourself, start with methane, start with ethane, and then keep adding stuff to it chemically. The burning of like your big lighter, for example, creating that black smoke. So that black smoke, as it goes into your house and then covers your roof with like a yellow color. You're been into a smoker's house before? Okay, and the roof is yellow. Well, that's haze on the roof. If you let that into the atmosphere, it forms layers. Okay, so we see that on Earth and we call it smog. You would not call it smog here. There are no cars. But it's very similar. You're burning something that's a complex hydrocarbon, right? And this is a different type of burning, but the processes are very analogous. Okay. So you can see the layering, and there's tons of these layers all the way through the atmosphere. It tells us a number of things. One, it tells us that the atmosphere is very calm. So if there are big storms on Pluto, all of that haze would get mixed up and you wouldn't be able to see the layers, right? And it tells us that the atmosphere is nowhere as thin as we thought it was. We thought that it was probably just going to be this little clunky rock, maybe a thin atmosphere. The pressure there is probably very low, but the extent, the physical size of the atmosphere is enormous. And you can actually see that because all the way through this photo to the edge of the picture, you can see layers of haze. Right? It's very rare that with something with a thin atmosphere, like Mars, for example, we'll see an example of that later. You don't see layers of haze all the time. Okay. Yeah, so here's what we thought from the solar occultation. So what that means, solar being the sun, occultation meaning hiding from it. So we saw the sun and then we watched the brightness go down to 0 while we were behind Pluto, and then we came back out on the other side. And remember I told you the shape of this piece as you go in, whether you go from directly here and straight down, that would be no atmosphere, versus a thick atmosphere would let you curve all the way out. So the edges of this data tell us how thick the atmosphere is. And so this is really what you should think of when you think of Pluto. Okay. This is about to scale. So Pluto's top of Pluto's atmosphere is bigger than us. Pluto's mostly atmosphere. You're saying that, what the fuck are you saying here? So, okay, so it's cold, right? So what that means is, even once something goes into the atmosphere, it doesn't get a lot of energy. It just stays a gas. And, you know, it's bouncing around, and it just like hangs out, bumps into its friends for a really long time. And it's not until it makes it all the way out here that it finally gains enough energy. It's like, I want to do my own thing. And it leaves Pluto forever. Whereas for us, you know, most of our atmosphere is stuck really, really low. I told you this analogy of taking a basketball and putting a piece of paper on it, right? That's the thickness of our atmosphere. Okay, it's just right there at the bottom. But then you can be a little, you know, let's say you're a little water molecule, bouncing around, seeing all your friends. By the time you get to that dotted line, then you finally have enough energy that you can leave and never come back, right? So Pluto's surface is being bombarded by light, being bombarded by all this stuff, and the ices are melting, essentially. If they don't go through the liquid stage, they go directly to the vapor stage, so they sublimate. And so that directly goes into the atmosphere, and once you've built the atmosphere, just hangs out a long time, bouncing around, making these beautiful hazes. Some of the hazes get so big they settle back down, and they color the Cthulhu region that really dark color, right? Which it all starts with nitrogen ices, carbon ices, methane, ethane, ammonia. Cool. Okay. Kind of ahead of schedule. Surprising. Like, that's rad. I don't know what to say. I don't have anything to say about this. Yeah. You don't care about that, right? Yeah. Yeah. Yeah, I mean, even Pluto, right? Like, you can see this from space. Like, this is not, how do I say this properly? This is with a normal camera. So this is a camera that was sent in 2004, for example. And the technology is probably from the early 90s because they had to make sure that it could survive the radiation of space. So it's not like the newest end camera when they launched it, right? So all the cool images that I've ever shown you is on like the dumbest technology. Like your iPhone in your pocket has a better camera than what we sent to Pluto. And yet you can see that. So just imagine, I mean, right now, finally the cameras are getting better that they're almost comparable to your eye, but still a sunset here is better than set on your phone. So I can just imagine standing there, hopefully in some sort of like warm protective bubble. And yeah, you would see tons of layers. And the layers are going to be really, really thin and really, really sharp. So even though it looks like very structured here, and like you could probably sit down and count them all, the places where it looks thick is probably like 15 or 16 all stacked up with little spaces in between them. That as you sit on the surface, it's just like, make sense? Yeah. Yeah, atmosphere's cool. Rocks? Ugh. Okay. All right, which body's which? Okay. Yeah. Yes, that is Titan. Very good. So Titan, remember, that was one of Saturn's moon. It's the largest moon in the solar system. And it has an atmosphere that you can fly in, right? Pluto doesn't, so don't get you excited. But the cool thing about Titan and the similar thing that you can see in both of these images is that here at the top of the atmosphere, see the blue color? It's blue for the same reason that it's blue on Pluto. There's complex hydrocarbons, they make hazes, except for on Titan, that haze gets mixed in with methane and ethane, and you get a hydrological cycle. So it's a little bit more. Okay. Okay, enough about that. Let's look at the other one. This is its friend. That's its moon, Charon. And even Charon has complex geology. What do you see? Where?
In the middle of towards the middle.
Oh, you mean this giant thing? Yeah, that's correct. Anything else? What?
Impact craters.
The impact rate is good. That's the easy one, right? Like lots of them. Yeah. Anything else? Where do you see erosion?
Like middle left.
Here? Here? Okay, yeah, so that could be, right, that could be erosion, that could be tectonics. Depends on if this thing is atmosphere. What did you say? Big brown spot. Yeah. Yeah, what the hell is that? No, that's a legitimate question, right? Why is it so weird and brown like that? No one knows yet. Cool. What about volcanoes? Have you seen any?
Like when you pointed at earlier, when she said with the erosion, like above it, like that's what we thought right there.
This one here?
So the other one next. Yeah, that,
This one?
let's say that might be a volcano
Okay, okay.
or a dead volcano.
Yeah, it's a little hard to see from this image alone. It certainly doesn't have a region like Pluto did that was just completely free of impact craters, right?
Some of the things that look like impact craters are not as circular, so maybe they're like, undergoing the same thing as Pluto, where the particles just immediately evaporate.
Yeah, so one of the things that we want to keep in mind here is we can tell when something is an impact crater versus not based on the shadows. So remember that impact craters always go down like this, and then volcanoes go up. So if I see, dark on this side and light on this side, with the sunlight coming from here, as opposed to if I see light on this side and dark on this side, that tells me if it's up or down, right? So I don't know if that's helpful or not. Most of these are impact craters, almost exclusively.
No, like in the bottom right one, there is one where it kind of does poke out a little bit. This one, right? Down one right there. There's some.
Yeah, this is really hard, right? And I think if we zoomed in here, with the actual data, we could see that there is certainly multiple impact craters in here that maybe weaken the crust. And sometimes you said, well, it's not quite circular, right? That's a very good observation because when we smash into ice, it's different from smashing into rock, right? Rock is really good at holding its shape, and ice doesn't always like to. It can smooth itself out afterward. So even though this thing is like big and round and even has a little piece in the middle that maybe looks like a part of a volcano, you probably think that because this is an ice, that it's an impact crater that's just eroded. Okay. Yeah, so tectonics, yes, I agree with tectonics. The problem with saying that any of these features are erosional or whether or not there might be volcanoes has everything to do with the fact that we already know there is no atmosphere. It could be that there was an ancient atmosphere. But since we don't see one now, it's really hard to make an argument that these could be those same type of words. We kind of have to use information that's not in the picture. What's this weird brown stuff? No, I don't think anyone dropped Pluto. So that material is from Pluto. So if you recall, this has a big old atmosphere. And at the very top, I don't know if I can zoom back to it here. I was talking about like the life of a molecule in the atmosphere of Pluto, and it gets liberated from the surface. It goes and it hangs out, really social for its whole life. And then it finally makes it out here. I'm out. Yeah, so then what can happen is it leaves, and maybe it backs into Charon. And remember the colors that we saw on Pluto, those brown colors on the Cthulhu region, same region, right? They have these really complex hydrocarbons moving from this brown looking planet over and landing on Charon. Now, why they're only at the pole? Hold on now. So this is how they look side by side. This is the image, right? So that's the one from the close approach. Obviously, this one has been colored. Let's keep that in mind. These are the enhanced colors. So if you go and you look at this, it's not going to look anywhere as red. Don't be disappointed. But what we think happens is that probably the atmosphere as it's leaving, it heads down towards Charon near its pole. Good. If you're really curious about that, we can talk after. Okay. As I said, no atmosphere for Charon. So that's what it looks like when there's no atmosphere. We head behind it, there's the light from the sun, and then it immediately goes to zero and then back up. Right? And contrast that with Pluto's. Right? So light, and then it's kind of not immediately to zero, and then to zero. Okay. Okay. Pretty cool. July 16th, 1965 was the first images we got from Mars. And then some number of years later, I don't want to calculate, hold on. 50 years later, we got the first images of Pluto. So you were alive for these ones. I doubt you were alive for these ones. I was alive for these ones, so that's. But now you can just think to yourself, what surface will they be taking images for the first time in 2065? That's soon, relatively speaking. Okay. So we'll just end the discussion of Pluto by thinking about Pluto in the context. I know. So this is one of many objects in the Kuiper Belt. There are thousands of them. And they all exist in, the same type of idea that we have about the asteroid belt. Think about that with the Kuiper Belt, but it goes farther. Objects are larger, and they're icy, right? These are the remnants of stuff that never made a planet. Yeah. Well, that's a wonderful question. I have a friend who works in KBOs. I will ask him. I assume that many do. The thing that you have to do is you have to so let's say there's a star over there. You have to wait for the object to pass in front of the star, and then you can watch the light be extinguished, just like we did with the sun. But that's kind of it's up to that object whenever it gets to a nearby star that we can do it to. So those are happenstance observations. I will find out how many have atmospheres. I would assume it's non-zero, right? I showed you last class. There are thousands of these objects. For example, Eris is larger and it gets closer than Pluto at certain times. Now it has a more eccentric orbit. It does end up going out and then coming back in again. So its atmosphere and its surface probably look very different. But we don't get to go visit Eris probably ever. Yeah.
Horizon just has it left the solar system?
No.
Oh no.
Oh, no. No. Solar system big. Solar system real big. And we'll talk a little bit about that when we think about the Oort cloud. We've gotten out to the second to last layer of the atmosphere here. These are the KBOs. And you can see, that was recent. Okay. So this is where New Horizons is. That was the inner solar system one. Oh, perfect. I have this here. Okay, so it launched in 2006. It immediately got to Jupiter. 1 year later, boom, Jupiter. That's hard to do. It takes 10 months to get to Mars. Okay, Jupiter is about twice as far. And so we got to the Jupiter system in 2007, and then 8 years later, got to Pluto. And it's just screaming out there. We're going to pass one more object, or I think we already did. Figure out what it's called. Oh, it's here. No, that's not the name of it. I'll find the name of it. Anyway, this object, we got a picture of it. Looks really cool. It's more potato shaped. Stuff in the outer solar system, especially if you're not big, you might be two small things that came and sat next to each other. And so then you look like a lumpy potato. That's not your fault. And then we probably won't go back to the outer solar system for some time. It's very expensive to get there. And it takes, like you saw, a really long time. So even when you think about, hey, I want to go visit Eris, right? Okay, so let's propose a mission to go visit Eris. Now, in order to do that, you need each of the planets to be in the right position that you can swing by them, so that you speed up when you go near them, and then that you use your rockets right as you're closest to them, to fire away from them. You need all the planets to be in the right position to get out there, otherwise it'll take you 20 years. No one wants to wait 20 years.
Yeah, I think that they do it Interstellar as well.
Yeah, that's how you get around in space. Because it's very expensive to bring fuel. Every kilogram that you bring for fuel is about $1 million. Yeah. So it doesn't take $1 million to make a spacecraft go. You can, launch them for 10 years or whatnot. But if I showed you the picture of New Horizons, you could see that there's a nuclear reactor on board. Right? So yeah, the type of work that you do in space is like, it's pretty cool. The cameras aren't, but whatever. Any other questions before we? Okay. How much did New Horizons cost the taxpayer? Oh, jeez. Not another clicker question. Not about money. Don't look it up. Don't look it up. I don't want the right answer. I want to know what you think. Better question. All right, click in if you're ready. Okay. Click in if you final answer. All right, so I only tricked 3 people with this answer. So there are more than 30 million taxpayers. In fact, there's close to like 300 million taxpayers. Okay. So then the question is, how much did it cost? Oh, I guess this one's not ready though. Just kidding. Forget those 2. So how much do we think it costs to go to Pluto? It costs $1 billion to go to Pluto. So it cost every American about $3. So why do we like space? Right? Why is America so good at space? We got a lot of taxpayers. Individually, $1 billion, like I can't come up with $1 billion. But if everyone pitches $3, you go to Pluto. What?
I said I don't know what dollars.
A week? Let's talk. Okay, I have a lot of ideas. So the thing that's really cool about the United States, right? Everyone, if you go to a place like Europe, go to a place like Africa, and you talk to people, you say, what is impressive about the United States? Inevitably, they'll tell you NASA. Not every country has a space agency. Not every country's space agency has been to the places that we've been, right? It's a real point of pride that we can do this. And then the amazing thing that they do, they give away all the data free. It costs nothing to download the data and you share it with the world. Because every image that we've ever taken of Pluto, I can show you where to download it. High res, perfect. Right? It's the idea that science should be infinitely accessible and it just costs the American taxpayer like less than a coffee. Right? When I made this slide, that was probably a coffee. Fucking inflation, right? Okay, so let's just really quickly do the Pluto summary, and then for the first time in our entire semester, we'll get out of here ahead of time. I know, relax. I'll get used to it. Pluto is a remnant of the early solar system. It is probably left over from all the material from which the planets that we saw are made. Something very similar to it was probably inside of Jupiter before Jupiter got its big body. You start off as one of these little cores, and then something miraculous happens in the outer solar system, and you make these massive planets. But if you don't have that miracle happen, then you're just left with these icy, rocky cores. Okay? So Pluto's great, but we'll see how cool these giant planets are later. It had a lot more geologic activity than was expected, right? And you need to remember this for this week's homework because we want to think about what is the driving reasons for that activity. Now, in this case, it wasn't tidal heating. There isn't another object that is giving it that. but it's the weirdness of ice, right? That ice does not behave exactly like rock does. And in particular, nitrogen ice, which we don't find basically anywhere else in the solar system, is the easiest to melt and deform. So it takes very little to make it turn into this weird churning ocean of nitrogen. Okay, any questions? Okay. Next week, we are going to have an open house. And at that open house, we're going to attempt to look at the little moon thing. Yeah. Live and die by the calendar.